Yes, we can start. So hello everybody, thank you for coming to SQLSaturday, thank you for coming to this session. I will talk about optimizing temporal queries. I'm Dejan Sarka. I will make a brief introduction in a second, just to tell you immediately that I am from Slovenia, so if you criticize, don't use theoretically implement them. Of course, Date, especially Date, is big theoretician, so he doesn't really work with SQL languages. He even suggested new relational language D. So this was really complete theoretical solution, but no practical solution yet, and it's definitely not any optimization. So in year 2000, three researchers from the Munich University, Kriegel, Petke and Seidel, finally described or developed first theory about the kind of specific temporal indexes that would enable more efficient temporal queries. When I talk about temporal queries, you can search for many different predicates, you know, whether two intervals meet, whether they have nothing in common or whatever. But I will focus on overlapping intervals. Already Alan has proven that overlaps operator is the most complex one. So it can be expressed with 13 other operators. So you need 13 other operators to express it if you don't have a specific overlaps operator. If you solve problems with this operator, with overlapping intervals, everything else is kind of easy. Okay? So we'll focus on this. So they also Kriegel, Petke, and Seidel defined queries and indexes that focused on overlapping intervals. Yet this was still only the theory, but first theory how to optimize these intervals. And the problem with this theory was that, yes, once you had indexes, it was alright. You could make queries run faster. However, they didn't find an efficient algorithm for building the indexes. So what they suggested was exponential algorithm. So if you have very deep indexes, it was impossible to build them. Okay. So in 2011 and from 2011 and 2013, Laurent Martin, a French guy, managed to find a linear algorithm for building those relational interval trees, those indexes that Kriegel, Petke, and Seidel suggested. So finally the theory was kind of developed. Now what about the other part, the implementation? So for SQL Server, I first wrote a chapter in this book, Inside SQL 2008, Inside SQL Programming, where I dedicated a chapter for a full solution for temporal data in SQL Server. So I implemented all of the constraints following completely the theory of Allen and Date and so on. Yet please note that this was before any optimization. So it was, let's say, a physical solution, but still with problematic queries. Okay? Now, my good friend and the guy with I wrote most of the books with, Itzik Ben-Gan, of course he was also in this book. Anyway, he took this optimized solution and got it in SQL Server in 2013, last year. So in 2013, Itzik has finally created an optimized Transact SQL solution based on these relational interval trees. And at that point, it sounded like, okay, finally we have the first solution. And at that point, I was looking at that solution and I didn't like it. So simple. I simply said, okay, first it's complex and then it's not optimal. And I will show you what I mean. I mean, it optimizes query, but not a lot. Also, a friend from Italy tried to use spatial data, which also gives some advantage. Still, I will comment, I don't like this way of not having strong typing, abusing different types. Okay, but it's, he also found a viable solution. And then in 2013, from July to the end of 2013, I actually managed to develop 4 more solutions that all of them kind of like better. So I developed both theory and the code, which you will see in a minute. So now I will say we have enough solutions for optimizing these queries. And on the top of that 4 solutions, I will show you also one which substantially slows down these temporal queries. So managed to find one which slows down, and also found one which I will not show, which was extremely great, worked perfectly in any situation, fast, just had slight problem that it returned incorrect row set. But otherwise it was great solution. Some people get picky and want to get correct row set, So let's go to this explaining what's the problem with classical Transact SQL solutions. Typically we represent intervals with 2 columns, begin end. Later I will show you also interval data type and you can represent this in a single column, but basically we represent them with 2 columns, and we represent time as time points, which can be represented, translated to integers. This is in accordance with Allen's theory, and this is also in accordance how do we work with time, if you think of it. We know that time is continuous, but we pretend that it consists of discrete time points. So we are talking about days, hours, years, whatever it suits our business problem. So we can always translate time to integers, and this is very typical and correct presentation, begin and end of intervals with two columns which are integers. So our problem, overlapping problem, is we have this table with columns B, E, and we have a given interval, search interval, like a variable, okay? And I want to get all intervals from the table that overlap with this interval. So this is the problem. And this is classic predicate. Two intervals can overlap when begin of one is before end of another one. If it's after end, definitely they cannot overlap. And also the opposite. When the begin of second is before end of the first one, then they can overlap. So this is the most classical predicate, which can be translated to classical where clause. So what is the problem with this where clause? You see, we can have two indexes. Best possible indexes in this case would be index on begin and included column end, or the opposite, index on column end and included column begin, right? But the problem is that we have two range predicates, and databases, whatever you take, will use only one index. So let's say that index that the key is the begin of the interval. This index can be used very efficiently if your searched interval is somewhere at the end of timeline. Imagine I have intervals in a timeline like this. So I'm searching some intervals that overlap with the interval somewhere here. So because I have index on begin of intervals, I can immediately exclude a lot of data. And even if I scan the rest, if I do partial scan, it's not a problem. Index on end column is very efficient in the opposite case, when the searched interval is somewhere in between, in the beginning of the timeline. However, when the searched interval is in the middle of timeline, both indexes have problems. No matter which one you take, imagine you take the one on the beginning, so you exclude left half of the table, left half of the rows, but still you need to scan the right half of the rows. And the opposite also is true if you take the index on the ending column. So queries that are searching for overlapping intervals in the middle of the timeline of all possible begins and ends in the table will always be inefficient. So let me show you this. Let me show you. So all of this code is already uploaded, and I already created a database and populated it in advance. You will see, because in commands you will see how much time it takes to populate using different solutions. So it's clearly that it wouldn't be doable in 1 hour everything. So first, this is the staging table where are just intervals, 10 million intervals that is used, so I have different solutions with the same data. Okay. So this is classical solution. We have ID and we have begin and we have end. So I simply populate this table from the stage, and this is how it looks like, right? And I have both indexes on begin and on the end column with included other parts and column for the begin index and the opposite. So I have all of the possibilities covered in an optimal way. So let's see the queries. So my intervals go from number 1 to 10 millions. So this is interval which is somewhere in the beginning, at the beginning of the timeline. Now let's look how it works. Everyone use option recompile just to be sure that it doesn't reuse the wrong execution plan. And what I get here, this is the most important part, I get 3 logical reads. Okay, you can see that index lower was used in this case. Okay, everything fine. If I go to the end of the data, the other index would be used, which isn't really important, right? And the important thing is that we have 3 logical reads again. Now what if I search for intervals somewhere in the middle of the timeline? Well, then I don't really care which index was used. You can even see that the more complex execution plan was selected, parallelized, because what we have is a large scan. We scanned about half of the table. So the whole table is nearly 23,000 pages, and we scanned half of the table. So this is the problem, and I don't really care which index was taken in this example. Maybe if we move slightly to left or right in the timeline, the other one would be used, but you see, it is always problematic when you are searching for intervals in the middle of the timeline. So now we know the problem, and now let's describe these solutions. Also, you saw, please remember those numbers. So we begin searching at the beginning or end of timeline. We came down to 3 pages, logical I/O, and the worst was 11,000 and something. So relational interval 3. Okay, this might be pretty complex. I will just briefly introduce the idea. Okay. And this is a virtual binary tree, so it's not really a balanced tree like an additional index. Physically, it is implemented like just one additional column, one integer. And the main idea is how to get this integer, and then you search this integer to get candidates for overlapping. So this integer is called fork node, and it is in the range of the beginning of timeline and end of timeline, somewhere in between. And it is the lowest possible integer that covers the actual interval. So we have a row, we have begin, end, and additional integer, which is the lowest possible that covers. Now, how does it cover? So it covers it when you calculate these fork nodes with bisection. So you have, in this case, I have intervals from beginning, the lowest begin is 1, the highest end is 31. Okay? So I start splitting this timeline into parts. And first I start with half of the, over the thumb, half of the biggest interval. So 16 covers all possible intervals. And then I split this in parts by section. So I go down. So like 8 covers this part, and 12 then covers this part. So for example, if I'm searching intervals between 9 and 11, 10 is the lowest number. So this is the fork node. Intervals between 9 and 15, 12 is the fork node. Also, for example, interval from 11 to 13, which in this case is shown, 12 is the lowest fork node. Okay? So once you have this number, then you calculate the fork node for the searched interval, and then you go and traverse this virtual tree. So physically it means a column in a table with additional non-clustered index on this column. So then you search for the candidates for overlapping, and you, let's say if you come to 12, you see you immediately excluded this part of the table and this part of the table. So this is the idea. The problem is that, as I said, Kriegel, Petke, and Seidel, when they discovered this, they didn't find any interesting algorithm how to calculate these fork nodes without recursion. Now imagine you have multiple recursive loops when you calculate for each row. So this is simply exponential algorithm, which means that it was impossible to use it. These are the formulas how to first calculate the root. Of course, we had 31, and then add 1, 32, and split by 2, and we get 16. Also the height, the number of virtual levels, can be calculated in advance. And then, as I said, fork node is calculated with bisection. So Laurent Martin, French guy, noticed very good logic with binary representation of the numbers, and found very nice logic how you can calculate from begin and end interval numbers, how you can calculate fork node with a simple formula. So you represent numbers in binary format, and you take matching prefix in bytes, in bits of begin and end. Then you add constant 1, and then you check how many bits there are, and you add zeros to the end. Okay? As many places as you need. So we have interval from 11 to 13. So matching prefix, this 11 is represented with 0, 1, 0, 1, 1, 13, 0, 1, 1, 0, 1. So matching prefix is 0, 1, right? And then you add constant 1. And we have 5 bits, so I need 2 additional zeros. So I have 0, 1, 1, 0, 0, which is exactly 12. This is a very nice trick which this French guy found, and this is actually the algorithm how to calculate it with Transact SQL. So this is the part that Itzik made in his article. Now suddenly this can be calculated in real time, and suddenly we have possibility to optimize these queries. Now imagine we have these fork nodes. How do we query this? So you see, we have multiple possibilities. So first we must go and exclude left side of intervals. So we have to traverse to appropriate node, right, to find the candidates for overlapping. So if I have node 12, anything, if I go to traversing this path, anything that is to the left of the ancestor of 12, this can't overlap. So I can immediately exclude those and come to these nodes. These are the nodes from the left of my interval that cover intervals that can overlap. Doesn't mean that they do overlap. However, all I need to do is scan the rest with original predicate. Right? I have to scan, and maybe you see interval from 9 to 10 doesn't overlap, but it's a candidate. The same thing is, so we get false positives. The same thing is then transferred to right side, applies to right side. So I must find all of the nodes which are to the right of my node, and all of those nodes cover intervals that simply cannot overlap. So I exclude them immediately. However, I still get, when I traverse down to the path, on the path to this node I'm searching for, I still get false positives. So again, I can get some intervals that might overlap but don't. For example, interval 14 to 15 doesn't interval with one from 11 to 13. However, as I said, I excluded a lot of intervals from the right and have to scan the rest. And finally, there can be also intervals that are covered with the same node. So 11, 13 also covers 10 to 14, the same fork node 12. So intervals that share the same fork node must overlap, no other way. So here we have no false positives. So the actual query will have to find candidates from the left, candidates from the right, and those in the middle that always overlap. So we'll have 3 queries joined with, union to a single result set. Right? On the top of it, to find these paths for right or left side, I still need to do a loop. I still need to do bisection. However, this is only once per query. Okay, so it's not so inefficient like it was initial building of the indexes. So let me show you this solution, and I will comment it immediately. So this is the idea that was developed in the slide, step by step, how you calculate this, this fork node. So I created this another table with node, which is simply a calculated column, and persist it. And then on the top of this table, I create 2 indexes for lower and upper search, and both have the key node and then begin or end of the interval. So this is how it looks like, ordered by node. So like node 22, node 16 covers interval from 7 to 22. Okay. We don't even need execution plan anymore. Now these are the functions that will find this path to exclude nodes from the left and right. So you see, this must be done with bisection. However, these 2 functions, left nodes and right nodes, will be called only once per query, so it's not such a big deal. So this is how it looks like. You see, let's say finding all nodes on the right side of the given interval. All of these nodes are on the right side of the given interval. Okay? So let's go and find intersection query, beginning of data. So you see this query is kind of complex. So I must find all of the left nodes and find all of the candidates, which I get with the join, right? And then I still need to filter out the false positives with the original predicate, part of original predicate. And the same thing is for the right side. Find all candidates and finally filter them out with the residual predicate. And those that share the same node, they always overlap. So let's see what we got. In the beginning of the interval, what we got is an error, right? Okay, now it's better. So what we got is, we got two logical reads in each function. Of course, this logical I/O cannot even cover CPU needed for calculation and so on. And 144 logical reads in the original table. Doesn't look too good because remember when we searched for an interval at the beginning of the timeline, we got three. The same thing from the right side. Again, we get, okay, more efficient. And in the middle of the data, this is the point where originally we had 11,000 logical reads. We still have pretty efficient solution, 144. Yeah. So we have a solution that kind of performs predictably. Okay. However, what is wrong with this solution? Well, I would say there are two issues with this solution. One issue is that it is complex. Complex code means also hard to maintain. Over time, developers change, and who will understand this code? So this is the first thing I didn't like about this solution. It is complex. Complex equals bad most of the time. Right. So the other problem is, look, yes, we got pretty much more efficient solution than 11,000 reads. However, I don't think it is the best possible. Remember that we got 3 logical reads in some cases. So now we have a goal. Simpler solution, and goal is clear. 3 logical reads. Anything beyond that is worse than is not optimal. Maybe it doesn't exist, but optimal solution would need 3 logical reads anywhere in the timeline. So, Davide Mauri is from Italy, and you know that Italians are similar to Balkan people, you know, very good for using things not for they are intended for. We have spatial data, so why would we use spatial data types and spatial indexes for spatial data? Well, we can use them for temporal data. This was his idea, and he tried, and he got pretty nice solution. The only problem is, of course, that spatial data types are implemented as CLR data types with predefined methods. Spatial indexes are covering areas. So spatial indexes are dividing areas into squares. And now if you think if I have interval in this area, interval is actually a line. I get a lot of false positives in the whole area. So I can imagine in advance that I will not get the best possible performance. However, the solution is out of the box. And yet I don't like solutions that don't use appropriate data types. It is a nice solution, however, abusing, also it's hard to maintain such a solution. Anyway, let me show you. So I just created ID and now geometry data type. And then I use geometry data type methods to get the geometry data type from text. And we get line strings and points. And please note that this was already populating this table. If you, I didn't show comments about time earlier, but I used like 13-15 seconds to populate this table with classical transact SQL solution and even with this relational interval tree. So the performance of the inserts and updates drops dramatically with this geometry data type. Still, think of it, it's not bad. I mean, 8 minutes and 30 seconds for 10 million rows is not really bad. It's pretty useful for many systems. Anyway, then we can create spatial index, right? And we need also some time for this spatial index, right? And with spatial indexes, we define also the granularity of these squares that cover the data. So the lower granularity means better queries, less false positives. However, it also means more time for creating this index and slowing down updates even more. Okay? So this is where you have to do some compromise. This is how it looks like, this table. Now this is binary, so it's binary stream, segment is stored in binary format, and this is how it looks like translated to human readable format, line string. Does this resemble you to anything? It looks like good, but to me it looks like a Polish last name typing. So let's now go and try to query this table with somewhere at the beginning of the data. So you need to use this geometry data type methods, and then you can query, and you get moderately efficient queries. You see, worse than relational interval tree, moderately efficient. Also, at the end of the data, yes, it's better than 11,000 logical reads. However, these queries are, as I said, only moderately efficient. And yes, there are also some other problems. Slow updates, not strong data typing. Space is not such a big deal. You see, if we execute this, we spent like 40% on the top of the original table. However, in addition to this, it is a SQL Server only solution. This is SQL Server's implementation of geometry data type. So the solutions has a lot of issues. Now let's go to my solutions. So, you know, if you think of it, what is a user-defined data type? You know, it has some predefined structure like begin-end, like this geometry line type, right? And the idea is because you have only one value, you can use only one index. This is the idea. So I was thinking in a very simple way. I need both values in a single column and with a single index, like spatial types. And this is what XML data type enables me. So I can store begin and end of the interval into a single column as XML, and then I have XML indexes. Looks great. So let's, even before slide, let's go directly here to the demo. So, you see, this is how you can create a simple XML with 4 XML clauses. So from begin and end, I can create XML data type, right? And XML value. And then I can even add XML primary index and index for properties and so on, right? So this was also slow to populate, little bit better than geometry data type. And this is now how the table looks like. And I have everything in a single column. So I have indexes, so we would expect, I expect it a lot, personally. I expect it a lot. So let's go and just execute maybe this one in the middle, and okay, let's go down so you will forget the comments. Well, what you see immediately is that query is executing, and it's executing, and it's executing. So you know, the full table was like 23,000 pages, so even, you know, scanning 23,000 pages should be finished in a second or two. Now this query is already 22 seconds and still working and working and working.
It's done.
It's done. It's done. Okay, let's check logical I/O. Whoa. 65 million pages out of original 23,000. Although the idea looked completely correctly to me, the implementation of XML data types and XML indexes is incredibly inefficient in SQL Server. I seriously don't know what SQL Server, and I don't even care what Query Optimizer is doing. Why is not simply scanning the table? No. What is it doing to get 65 million logical reads? So this was I count this as my personal record, you know, when optimizing the query, making it 7,000 times slower, this is kind of a personal record. And on the top of it, also look at the space used. It's now like 9 times more than original table. Okay. So it looked a good idea to me, but you know, the implementation was a shock. And this is you know, also better than geometry because XML is more standard, geometry is SQL Server only, and so on. Unfortunately, it is completely useless. So you can do a lot with XML optimization. So my colleague from Slovenia, Matija, took really his time to do all possible XML optimizations and got to only 8 times slower solution, not 7,000. In general, what does it mean? You know, the conclusion is stay away of XML data type in SQL Server and definitely don't index it. Without an index, you would still get at least scan, you know. In the XML indexes completely confuse query optimizer. Okay, so now let's go to more useful solutions. This is the one I love the most. You know, when I found it, it was July last year, and it crossed my mind, why couldn't I do it this way? It was so simple that I couldn't believe that nobody in the world didn't think about this solution yet. It's so incredibly simple. And then I used a lot of time for Googling, you know, I don't want to be accused for plagiarism or something, you know, stealing the ideas. And I didn't find it. So apparently I was the first, or at least the first one who published this. I didn't find it. Okay, maybe there is somebody, I don't know, in India, China. But, okay. So what is the idea about? Well, you know, remember relational interval trees. I work a lot with associations. This is a good way how to get the ideas. So relational interval trees, when we browsed candidates from the left and from the right, we got false positives. But we didn't care because we excluded enough those that are not candidates for overlapping. So I was thinking, when we were writing where clause, we are always thinking in one direction. We want to get exact matches. Why wouldn't I try to do approximate where? Similarly to these relational interval trees, where clause that would simply exclude enough of intervals that the query would be efficient even if I have to scan the rest. And of course, in this where clause, I need to use only one index. So let's focus for lower index on the beginning. It is also possible to do the opposite. I will just show you this graphically. So you see, what are the idea? What I've got here, black are intervals in the table. This blue is my searched interval. And this is important. This is important. It's so important that it disappeared. So the red one is important. This is the longest interval in the table. Now what was the idea? You see, I'm using index on the beginning of the intervals. So, if you remember the predicate, beginning of one interval must be before end of another. So if I look here on the right side, then this predicate is extremely useful. Any for the lower index, any intervals that begin after the end of my given interval, just one time point after the end, are excluded automatically. This is same predicate as we had with the original solution. What about the left side? Well, my idea was simply, let's go to the left enough that I get only intervals that cannot overlap with my interval anymore. So how far it is? Well, simply, let's take the beginning of my interval and go to the left for the length of the longest interval. So anything that starts before that, starts, not ends, cannot overlap. Now, with this predicate, I simply exclude all of those intervals. And I get false positives here. So I still need the original predicate to scan this part. That's a very, very simple idea. So let's see the solution. And then we'll also comment it. Has anybody any idea what could be a problem with this solution? Exactly, exactly. So yeah, this could be the problem. So let's see. With this, in this demo data, it is not the case. And this, no, seriously. So I have begin, end, and I will also persist length just to make more efficient queries to find the longest interval very quickly. Anyway, if I know this length in advance, this the length of the maximal interval, if I know in advance, then I even don't need this value. So, for the beginning of the interval, first I must find the longest one, which is maximum of the current interval and the longest in the table. Even the searched interval could be longer. And then, you see, this is the original part of original predicate, begin in the table lower than end of the given intervals, and end greater than begin. So this is the original predicate. And this was added on the top. This is to use the left index, and this is to use the right index. I don't know which one will be used. Let's maybe check. But let's see what kind of query I get. So, okay, first this is to find the maximum, and then it's just no cluster at index 6. In this case, it was used the lower, index lower. And what is the number of logical reads? Well, it is 3 to get the maximum length, and it is 3. This is the optimal way to get the actual intervals. And it works also at the end of the data, and of course it also works in the middle of the data. So this is actually, in this case, the optimal solution. The actual logical reads, I need to find the intervals after I get the interval of maximum length is 3. So, but please also note, forget about this calculating the maximum length. Look at the query. It's extremely simple. Remember the original query? I just added 2 predicates to the where clause. That's it. And suddenly I get extremely efficient query. So this is why I couldn't believe that nobody has thought about this option in advance. So it's extremely simple, yet extremely fast. And what is the problem? Yes, you noticed. So you noticed immediately. Yes, the problem is, what if this longest interval is extremely long? Then you see, then I would need to go all the way here, so I wouldn't exclude any intervals. So in worst case of very weird distribution of length of intervals, I would get similar solution to classical transact equivalent. Could be inefficient in the middle. Now, you know your data, okay? So you know your data, and in many cases, the distribution is pretty regular. You know, if we are talking about contracts, we typically have 1 year, 2 year, 3 years contracts. We don't have a contract for 900 years. Right? We typically don't have this. At least, okay, in most of regular businesses, I guess it's similar, like in Slovenia, if some politicians are making contracts and are bribed, then yes, then you could get 900 years contracts, but in regular cases it shouldn't be like this. So, also, what is good about this solution is that you really don't need to invest much in your database. I mean, you are just changing, compare this to relational interval trees. You are just adding two predicates to your where clause, and that's it. And that's it. You don't need to do anything else. Indexes are original. Okay, and of course, yes, you need to know the length of the maximum interval. But you see, so it's extremely simple and extremely efficient. Yes, it depends on the interval length distribution, but in many cases in real life, this distribution is pretty uniform. It's not so weird. Even if you have one interval that is extremely long, you can then make more complex solution and first check for this interval and then for others. Now, in this Inside SQL Server 2008 Transact SQL Programming, in the Temporal Data chapter, I also developed the interval SID I called data type. Didn't want to call it interval to prevent mess with the theory. So it's interval on countably infinite discrete sets. And I implemented all of these L&S operators. And this is CLR data type, so it's binary ordered in my database. So this would be the order, like interval 1 to 5 would be before 2 to 2. This is how SQL Server by default orders CLR data types, if you don't implement some custom ordering. So anyway, this varies with this data type once you have are very, very simple because all of these operators are implemented there. Yet the problem is that queries are not efficient. So let me go to demo, and as I said, I will not go into all of the details. I will not develop this, redevelop this data type. It's already developed. So all I needed to do was deploying the assembly in the database, and then create the data type, and then I can use it. I can simply use it, so instead of begin end, I have during from 2. During, which is this data type. And you see that population was very efficient, much more efficient than with geometry or XML, of course. And yes, geometry is also a CLR data type. Why is then so much slower? Well, the answer is very simple. Geometry was written by Microsoft. This was written by That's it. So this is how it looks like. So we have, similarly to geometry, we have binary strings, right? And this is the string presentation. Now let me show you the query. I will focus in the middle of the data. This is my given interval, right? And the query is extremely simple. I have overlaps operator in my interval data type, and that's it, it works. However, wow, what happened is, yes, full table scan happened. So with CLR data types, SQL Server didn't know how to optimize the query. At least it was not confused as with XML, so it did full table scan. Simple query, very nice, but inefficient. However, we have the same solution as with enhanced Transact SQL. I can add where clause. Right? This is the same, similar thing as with enhanced Transact SQL solution. Just that now I have in the Transact SQL solution begin end, I had 2 indexes, lower upper. Now I have only 1 index because I have all values in a single column. So it's sorted by begin. So this is equivalent to this query that excluded from the left those who are begin, where begin is before begin of current interval plus length of the longest interval. It looks more complex code, but it's not. I just need to convert integers to intervals because I'm working with interval data type. I cannot work with integers. And then what happens is, With this simple addition, I get extremely efficient queries again. So on the top of enhanced transact SQL solution, I have now really strong data typing, custom level data type, all of the methods. Very are simple, just a little bit modified workflows. So I kind of like this solution as well. And it has the same problems as this enhanced transact SQL solution. One very long interval could spoil the performance substantially, but it cannot be slower than the original transact SQL solution. In worst case, it can still, it would scan half of the table. Okay. So this is this. Now the next solution is my favorite. It is not just because it is efficient. The enhanced transact SQL, I like it also because it's very simple. But this is, you see, if you would read all of the theory and the implementation I did in this transact SQL 2008 book, you would see that I'm using this so-called unpacked form a lot also for constraints. So at that point I developed this forum because I wanted to implement constraints in a simple way. And I managed to do it very efficiently. Very efficiently from the coding perspective. Simple code, yet inefficient from performance perspective. So I needed additional 5 years to find, to realize that this forum is also extremely useful for optimizing queries. So you see, we can represent intervals in different ways. And with different presentation, we still cover the same time points. So we have these intervals from 2 to 5, 3 to 7, 10 to 12. And you see these first two overlap. So I can represent them in a different ways. So, for example, I can expand all of the intervals to unit intervals and select distinct unit intervals, and I'm covering all of the time points from 2 to 7 and from 10 to 12. So these intervals cover the same time points as this. Also, I can convert them into more compact forum. So these two that overlaps are union to a single one. Anyway, this is the definition of these two forums. Unpacked forum is the most expanded one, when all of the intervals are expanded to unit interval. Okay, the unit interval was the word. And we have only distinct unit intervals, and the most compact forum, the most possible compact forum is packed forum. Now, packed forum is not really interesting for me in this case, although I use it for some constraints, but unpacked is extremely useful for optimizing queries as well. So my first thought was why I prefer this. I need it anyway for the constraints. Please read the chapter, what kind of constraints can you solve. So if you really go and implement intervals correctly, you already have it. If you implement full constraints, you already have it. So that's why I love it. If you don't implement, most of solutions nowadays don't implement all constraints that they would need to implement in a database. There are probably many developers here who are using abusing SQL Server as flat file and so on, okay, right? But I will not go there, I don't want to start some fight now, okay? But if you really want to implement all of the constraints, you would already have this forum. The problem is how to find this forum. How to find this forum? Well, you must create enough rows for every interval. If interval covers 5 time points, you must create 5 rows. We have integers begin, end. How do we create rows? Simply by a join. Joining to what? Joining to what I need is a simple table of numbers. Sequential numbers. And then I can quickly create this table or this unpacked forum. I can create it either as an indexed view, so it's updated automatically by SQL Server, or as a table, which can then be updated manually through triggers. But this table could be compressed and so on, which you can do it, and you can use all kinds of operators then you can't use, for example, apply operator in a query if you want to create an indexed view on the top of this query. So let me show you the solution. So first I created simple table of numbers, right? Populated it. These are simply sequential numbers, and this is classical transact SQL solution. And on the top I created a view which joins intervals to the numbers table, where number is between begin and end. So I get enough rows for every interval, and then index the view, and then inserted the data. So with this index view, insert was slower, much slower than original, still faster than XML spatial, still pretty good. And this is how it looks like then in unpacked form. So I have ID and all of the time points that are covered by this interval. Now the problem is that, of course, unpacked form takes much more rows than original form. So from 10 millions I came to 110 millions. Okay? But please note that this is very narrow table, so it's not occupying that much space. It's very narrow, it has only ID and 2 integers only. Okay?
Is it possible to use seconds, for example?
It's just, look, these are integers, so the context is up to you.
No, the multiplication of rows.
Seconds.
Yes, so...
Yes, you can say my integers represent seconds or days, whatever you wish.
The table will become...
Yes, the table will depends on your granularity and the length of the interval. Your granularity can be also a year, but if you have billion years long intervals, you are in the same problem. So the problem is how many time points these intervals are covering. And yes, this is the problem of this solution. But once I have it, you see, once I have it, I can make extremely efficient queries. Nearly the best possible. Here is 5 logical reads. Let's go somewhere in the middle. Somewhere in the middle. And what I get is, okay, 5 logical reads. So extremely efficient solution. I can even make it more efficient if I create a table and then use data compression and so on. And then even it's more, you get faster updates. You get faster updates. Now, even with this table, we get extremely efficient queries. Okay? Just you now query the other table, not the original one. And yes, you noticed the problem with this solution. This forum has a lot of rows. Still, I think this is the solution for which will overwhelm all other solutions. You see, your intervals are already there. So you know the amount of rows we will generate. So it's a constant problem. Constant and linear problems, how do we optimize those problems? Simply with hardware. If you can't afford billion rows now, you will be able to afford in 10 years or in 3 years. So that's it. Nothing special here, just need some time. And then everything works perfectly, right? However, what if you have now, and think of your intervals, like if you have contracts that are 1 or 2 years long, then you work on day level, not on second level. So you have like 700 possible rows from one interval, so it's not such a big deal. And as I said, this is a constant problem. Yet, always I'm talking about this, somebody says, yes, but this is the problem. So here is the last solution. The last solution, which I wanted to call packed unpacked forum, but it would sound too much like an oxymoron, so I call it compact unpacked forum. And I don't like this solution. I will tell you in advance, I don't like it. It is more complex and so on, and the only reason I went to this is because everybody said, yes, but unpacked forum has so many rows. Just wait, be patient. That's why I went to this. So I was thinking, like, you know, let's say when we are calculating time, like how many time is from now to I don't know, 25th of November 2025. So we don't calculate, we work on day level, but we don't calculate days. We use bigger units. We start with years. So it is 11 years, 2 months, and then we come to days. So I was thinking, can I get this idea in intervals as well? So let's say I have this interval from 19